Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Flex Logix with Jayson Bethurem. I'm going to talk today about adapting to evolving IC requirements. Jason, what's driving the big changes these days in how you design a chip and what's going into them?
It really comes down to how flexible and adaptable our world needs to be. We can think of application solutions like packet processing and smart NICs and how that's evolved over time, all the way to the other side of the spectrum with security and how those evolving threats continue to compromise the chips that we're building today.
Let's take a closer look.
Great.
Jason, what are we looking at?
What we see is a lot of these applications requiring adaptability because of either evolving protocols, encryption models, algorithms, and so on and so forth.
And so you think about each one of these. Let's take these one by one. Interface flexibility has been a huge problem because one of the problems that you're dealing with these interfaces, they're almost in constant state of flux. You think about UCIe and CXL, all those things are changing, right?
Right, and it's not only a function of just these protocols like UCIe, PCI Express, and other things changing like that. It's as simple as just being able to adapt to more protocols for your end market and your end customer, whether the customer needs more, even low-speed interfaces, whether SPI interfaces or I2C or UARTs. It's become sometimes as simple as that, all the way up to the higher level protocols you're talking about that just keep evolving and adapting over time.
Taking your next item here, software acceleration. Most people associate software acceleration with FPGAs. They're very good at that. What's changing?
You're right. Nobody disputes that FPGA technology is great for accelerating software algorithms, especially ones that are pipelined and require parallel processing in nature. What's changing is the economics of scale of FPGAs and the complexity of FPGAs is growing, and they're becoming more complex, bigger, and require more power and are more costly to implement in the system. Most applications only require a small piece of this software algorithm to be accelerated. Therefore, integrating a small piece of programmable logic into your IC can provide those eFPGA benefits without the cost and power associated with a discrete FPGA.
But you also have to now work your way into this design, right? And most people are not thinking, oh, we can put an FPGA in here and it's fairly small.
Yeah, scalability is critical, and that's where embedded FPGA programmable logic solutions are offered in these types of things. We can actually build logic arrays down to even just a couple hundred LUTs, all the way up to hundreds of thousands, even millions of LUTs to solve whatever complex problem comes your way.
Really, what you're doing here is adding scalability into FPGAs, right?
Correct. It's not just into necessarily an FPGA, but it's into your IC. Bringing that embedded programmable logic FPGA technology into your IC is critical, and everybody's design requirements are different. As I stated, larger complex algorithms may require a bigger logic array, which scalability to provide that to a customer exists. And now what's really important here is that an embedded programmable logic array can scale to virtually any size you need. So you're not buying a discrete off-the-shelf FPGA that's of X size and you only need 20 or 30 or 40% of that. You can now scale down to exactly precisely what your design requirements dictate.
That also works in security as well, right?
Absolutely. Security algorithms are quite diverse in what they can do. We can actually take, for example, an AES core and implement it into a very small logic array inside of our IP that you can instantiate in your device. Now, just an AES algorithm core is just one example of all the evolving security protocols that exist there. And crypto agility is something that we all have to be concerned about because decisions we make about security today will certainly be inevitably wrong in the future. And especially with solutions coming out with quantum compute solutions, we need to have ability to have flexibility to adapt to whatever evolving threats that come at us in the future.
So you're scaling security in two directions, one of which is over time, and the second one is how much security do you actually need for this particular device and this data?
Great question, because not only are you securing and authenticating your data and your sensor input sources, but you're authenticating data flowing through your system and outbound to other sources downstream. But security can't be just thought about data alone. Security can be applied in different ways as well. Consider the fact that we can take a chip and obfuscate pieces of the IP inside of the design. So I always like to use the Coke reference. Nobody knows the entire Coke recipe. There's one secret ingredient nobody knows. Obfuscating that piece of IP in your design can give you that kind of security that you need to for sure nobody's going to clone or break or steal your IP.
You have another element in here too, which is that the longer these devices are in the field, they also age. And as they age, they start closing up lanes, they start getting electromigration. You can now reroute some of those signals as well too, right?
Yes, you can think about that, and especially in networking applications where the data throughput is so significant. Not only can we redirect signals to different pieces of architecture inside your IC, we can also manipulate the data so the data is not flowing through your IC. We can actually reroute data. A great example of this is in packet processing with the distributed denial of service attacks that happen where servers are just bombarded with endless amount of data. If we can quickly, on the front end of that packet processing pipeline, detect that data is malicious and prevent it from entering the chip, that downstream events do not happen, therefore preventing some of the issues you're talking about, as well as just not bottlenecking the server on the back end.
There are certain things we know FPGAs do well, things like filtering, transforms. How does this apply now into the world of AI?
Fundamentally, the building blocks that build those signal processing algorithms, whether it's filtering for FIR or doing FFTs, all those building blocks lend themselves directly to AI applications. And what really makes that marriage so great is not only the combination of high density and a high amount of multiply and accumulate modules inside the block, but also locally coupling memory to those blocks. Without the tightly coupled memory, you don't have the coefficient storage, you don't have the acceleration that you need. Now, in tensor applications, it's virtually the same type of application, except you have multiple layers of these MAC blocks and more tightly coupled integration of your memory, because not only do you need the coefficients for the weights of all the neurons or the nets, but you also have the activation functions as well you have to store. So building these types of applications in this really highly distributed architecture is very valuable.
And really what's happening here is that you've got more data than you did in the past, and you can't move all of it because moving that data is both resource intensive and also costly. So now you have to do more of that processing in multiple places, right?
Great point, yes. The fact that nobody can deny that we're being bombarded by more data now than ever. So having the ability to process this in parallel. And by the way, every task that you get, every piece of data that comes in is not homogeneous. Every piece of this data has a different application or requires a different algorithm to process it. So having that algorithm diversity, think about a programmable piece of logic in here where you can change that personality of that logic every time that new packet comes in and that processing changes. That's the most efficient utilization of that time and processing window to get that data in and out and rerouted or processed in the way it needs to be. So having that adaptability is critical in those environments.
Basically, you need to be a traffic cop for what's coming in, right? This is your partitioning and prioritization role.
I feel like these days when you look at network switches and smart NICs and things like that, that's exactly what they are, traffic cops. Again, the network is just being bombarded by so much data, as we've talked about. And I read a statistic some time ago where somewhere around 30 to 40% of that network traffic now is malicious in nature and somehow, or it's artificially generated in some way. And so being a traffic cop is definitely a good description of that, because if we're not really creative and intelligent on how we're mitigating all of that, it does slow down our reaction time, it does slow down our processing, increases our latency, which effectively is a bad user experience, and it could be devastating user experience.
We tend to think about data in terms of packet processing, but we're also dealing with much larger things these days, images, video, streaming, right?
Yeah, exactly. So not only do we see the data coming in different formats, like I said before, data comes in, you have to react to whatever type of data it is and apply the right algorithms. Image signal processing, whether it's coming from surveillance cameras or your iPhone, even just being captured from a person playing a video game on the network, that data all has to be interpreted differently. But in an ASIC, for example, too, the front edge, the edge processing of this, the more of the front end signal processing you can do of that data is very critical. And again, I just mentioned 3 different environments. Think of it as an automotive scenario where a car is looking out, whether it could be nighttime or daytime, and the environment's changing all the time. that front end image signal processing chain has to be able to adapt to that environment wherever that car may be. Same with a surveillance camera, could be snowing outside, could be raining, could be overcast, could be sunny. You have to have a very highly dynamic image signal processing chain to adapt to all those different environments. That kind of flexibility enables greater adaptability in all of those market conditions.
Jayson Bethurem, thanks for a great explanation.
Thank you.